We're going to go through chapter 12, and we're going to start by talking about atoms, elements, and the things that make up your atoms and elements, which are protons and neutrons. So to begin with, we'll talk about atoms. You've probably heard the word atom before, even if you haven't taken chemistry, and it is the smallest particle that has an individual identity so far as a substance that it becomes. They make up all the matter around you. You'll find atoms in the air, atoms in the computer that's in front of you, atoms in the water that you drink, and they combine in various ways to make the compounds that make up everything around you that you see. They're made up of electrons, protons, and neutrons, which combine in various combinations to give you your different atoms. And they come from reactions of the stars, most of which have died out and left behind the matter that you see around you. So the various parts of the atom, there's first and foremost a nucleus, which is found in the center. It's very tiny, very compact, and it contains all of your protons and neutrons. And we'll talk about what those are in a minute. And then around that, you have an area that's mostly empty space, but within it, you'll find your electrons. And so that's called your electron cloud. Now, those electrons all have negative charges, and because they are negatively charged, they tend to repel each other, just like the two south poles of magnets would do, push each other apart. So they take up a vast amount of space surrounding your nucleus. The elements are the different types of atoms that we have. And there are a little over 100 known elements. Only 90 of them are actually found in nature. They've made ones that are bigger than what's found in nature in the laboratory, but those tend to be unstable and don't stick around for very long. The others are fun to study, but there are various reasons why you get to a big enough size that they're not stable anymore. The elements are the basic building blocks of everything that you find on Earth. So some examples of some elements. A diamond is made up of carbon that's built into this really beautiful lattice, and it becomes very strong because of how those carbons are connected, and carbon is a type of element. You could also take carbon and connect it in sheets, and when you connect it in sheets you get graphite, which is what is found in our pencils today. It's what leaves the mark behind as you're drawing. Then you can also have carbon that is in a chunk, and those chunks we call charcoal, and we burn them for fuel. So carbon comes in lots of various types, just as carbon itself, and how it is connected determines the properties it has. Helium is probably an element you're familiar with. We put it in helium balloons and they rise. We used to put hydrogen long time ago because it's actually lighter than helium, so the balloon would rise farther and faster, but hydrogen is flammable and helium isn't, and so they switched to helium as what we use to fill balloons. The Hindenburg was filled with hydrogen. It was a blimp, and it lit on fire and burned down because it was full of the hydrogen. So oxygen is found in the air we breathe. Actually, most of the air we breathe is nitrogen, about 70%, but oxygen is the next most prevalent element in there, and it comes in twos, and so you're breathing O2, and then that gets into your bloodstream and keeps you alive. A bar of silver is found off to the right here. Those are all silver atoms. When they are pure, your metals tend to be really soft, which is why you'll find if you have a gold ring that it doesn't entirely gold. They tell you it's got some amount of carats, which tells you how much gold is actually there. If it were purely gold, it would be malleable. You could like squish the ring on your finger, and that might not be a good thing. So here's a periodic table of elements that I found on Google, and if you look at the various elements here, you can pause it if you want. They've got examples of things that you're probably more familiar with that have to do with each of the elements. So For example, they have oxygen drawn as an oxygen atom. They have helium as helium balloons. They have phosphorus and a lot of its compounds that have pretty colors in them. Sulfur is usually yellow. If you've ever been to Yellowstone, you can smell the sulfur there when you get around the various things there. So it shows you all of these elements in ways that might be familiar. But the real periodic table, the one we use every day, looks more like this. You'll notice that they have a symbol for each of the elements. So our example here is carbon in their example one that they're showing you. And then they've got an atomic number up top and the atomic weight down bottom. And then you'll notice this one's color-coded to show you the metals, which are most of the elements on the periodic table, the semi-metals, which are the green ones, and then the non-metals, which are the yellow ones. And you'll notice hydrogen is also a non-metal, even though it's kind of located apart from everything else. There are a couple that are white. Those are ones we've created in a lab, and they've never existed for long enough in large enough quantities for us to determine that they are metals, although there's a good chance that they are. So your atomic symbols can come in a variety of ways. They are always made of one or two letters, and the first letter is always capitalized and the second one is always lowercase. Now that's really important because you have some that the second letter, if you were to capitalize it, it would actually be a different element on the periodic table. So be sure that you follow that whole thing of the first letter is always capitalized, and if there is a second, make sure it's lowercase. So for example, H is hydrogen, He is helium, C is carbon, and O is oxygen. There are some that are not as intuitive as that. You'll notice most of those that we just went over is the first letter or the first two letters. For example, lead is Pb. That's not usually what you'd guess lead would be, but it comes from plumbum, which is the Latin name for lead. K is potassium. That comes from kalium, which is the medieval Latin for potash, which is where they found potassium in medieval times. So you'll find a few of them that are counterintuitive, and you'll just want to be careful because sometimes people start mixing them up when they don't really make sense right off. Your protons and neutrons are the particles that are found in your nucleus. Because they're found in the nucleus, they're called nucleons. Your protons, we'll talk about those first, have a positive 1 charge. They're 1,836 times heavier than an electron. So much heavier. Why does this matter? Why am I even telling you this? Well, if I were to put you on a scale and weigh you, let's say you weighed 150 pounds. And then I had you get off the scale and I touched you and I left a particle on you like maybe a bacteria. Really tiny, doesn't weigh a whole lot, but it does have mass. And then I ask you to get back on the scale. Chances are you would once again weigh 150 pounds. And this is the way atoms work. Although we have protons, neutrons, and electrons in an atom, an electron is so light compared to everything else that when we start talking about the mass of atoms, we very rarely worry about the mass of an electron because it's so much smaller than your protons and neutrons. The purpose of a proton, they actually stabilize neutrons and they also attract the electrons. Because they're positively charged and electrons are negatively charged, positive and negative charges attract, and so those protons keep the electrons in your atom. The number of protons is what determines what element you have. So if you have 1 proton in the atom, it is always hydrogen. If you have 2 protons in the atom, it is always helium. If you have 3, it's always lithium. If you have 8, it's always oxygen. If you have 9, it's always fluorine. If you look at a periodic table, you'll see that these are the numbers above the element symbols. And they're also the number of protons. It's called your atomic number. So, for example, Fe is iron, and that would be 26. Uranium, which you may have heard of before, has 92 protons. You don't need to memorize these numbers. You'll be able to look them up on a periodic table. But you do need to recognize that that smaller number in each square of the periodic table is the number of protons and is also called the atomic number because that atom is based on the number of protons written there. The neutrons don't have a positive or a negative charge. They are neutral, as the name probably suggests to you. They're 1,841 times heavier than electrons, so just slightly heavier than a proton. Their actual mass is 1.675 times 10 to the negative 27th kilograms. And their job is to stabilize the protons in a nucleus. So once you get more than one proton in a nucleus, you're putting positive charges next to each other, and they would tend to repel. We'll talk about the attraction that keeps them together so that they don't. But the repulsion is going to be strong enough that you need a neutron to help out in stabilizing them together. And there's one element that only has one proton, that's hydrogen, and most often it exists without a neutron because it doesn't need anything to stabilize it since there's only one positive charge there. The number of neutrons is usually roughly about the same, but it can vary in either direction by a few, and because of that you can have a type of atom that has different numbers of neutrons. If you were to take a sample of them and sample them, they may not all be the same. They would all have the same number of protons because that's what makes that element, but the neutrons might be slightly off one way or the other. So for example, hydrogen usually doesn't have any neutrons because it doesn't need them. But occasionally in nature you'll find that it has one neutron along with the proton. And sometimes, most often because we created it this way or because it's coming off of radioactivity, it has two neutrons. When it has one, it's called hydrogen. When it has two, they actually have a special name for hydrogen. This is only the case with hydrogen. When it has two, they call it deuterium, and when it has three, they call it tritium, when it has three nucleons. So one nucleon is just going to be a proton, two is one proton, one neutron, and three is one proton and two neutrons. And each time it just has one electron because you only have one positive charge in the nucleus to counteract. So when you have various numbers of neutrons, they call the different types of species isotopes. So they vary in their number of neutrons, but they're the same type of element. So they have the same number of protons. So they would be called hydrogen or helium or lithium, as you see off to the right here, because of the number of protons. But the number of neutrons can vary, and it's still that element. So they vary in mass as well, because remember, each neutron weighs about the same amount as a proton, so you're adding mass each time. So the hydrogen here has the one proton. It would have a weight of about 1 times the weight of a proton. Sorry, one proton. Then you have one proton and one neutron with H2, so that's going to have a mass of about 2. And tritium here is going to have a mass of about 3 times the mass of one of the protons. You have helium here. They've got 2 red dots here. Those each represent a proton because helium has 2 protons. And then you have 1 neutron there. That's helium-3. That's less common. And then we've got helium-4 here, which has 2 neutrons and 2 protons. And that's going to have a mass of about 4. Lithium, you have 3 protons in both of these, otherwise they wouldn't be lithium. But you'll notice one of them is lithium-6. It has 6 nucleons for a mass of about 6 times the mass of a proton. And then lithium-7, they have 4 neutrons here for a mass of about 7 times the mass of a proton. So these vary in mass, but they don't tend to vary in reactivity. Sometimes in nuclear chemistry they'll be different, and we'll study that in another chapter. So the atomic mass is the total counted number of nucleons, and it will be equal to the protons and the neutrons for an isotope. Often when you have an isotope, it's written with the element name, such as carbon, and then they put a dash, and then they write the total number of nucleons. So carbon 14 is going to have 14 nucleons. If you look up carbon on the periodic table, you'll notice there's a 6 above it. That means it's going to have 6 of them that are protons, because carbon always has 6 protons. So if you do the math, what number plus 6 would give you 14? You'll say 14 minus 6, it gives you 8. So that means the other 8 are going to be your neutrons. So that particular isotope would have 6 protons and 8 neutrons. It can also be written with the mass number on top and the atomic number beneath. So here we have lithium. This is lithium 7, so they've got 7 over 3 Li. Notice this is the opposite of how they typically write it in a square on the periodic table. Instead of having the atomic number at the top like it is on the periodic table, here it is written on the bottom of your symbol. So you'll find isotopes written either of these two ways. When you look at the periodic table, you'll notice that they don't actually have one isotope. They've actually got an average there. So when we're doing the math from your isotope symbol, remember that the mass number is the top and the atomic number is the bottom. If you ever forget, the mass number is always the bigger number and the atomic number is always the smaller number. So you can just go off of that. So the A is your atomic number. That's your number of protons. Really easy. If we want to know the number of neutrons, though, it isn't quite so straightforward. We have to take the mass number and we need to subtract out our atomic number. So if we want neutrons, we take Z and we subtract A. And the Q right here just represents whatever the element symbol is. So you could plug in your element symbol there. So on the previous slide, we had 7 nucleons. And we subtract 3 for the lithium, we get 4 neutrons in our lithium. So that lithium was made up of 3 protons and 4 neutrons. So the atomic mass on the periodic table is rarely a pretty number. You'll notice on sodium here we have 22.990. There isn't actually a sodium that has that mass. What those masses on the periodic table are is they take all the natural elements, the ones that actually exist in nature, and they take a sampling of them, and then they take a weighted average of the masses. So most of our sodium has an atomic number of about 23, and a little bit of it has 22. When we take that little bit at 22 and that large bit at 23, they average out to give you 22.990, which is closest to 23, but not exactly there because it's pulled down by the lighter isotopes. The atomic mass given here is in atomic mass units, and the atomic mass unit is 1.661 times 10 to the negative 24th grams. So it's slightly less than the mass of 1 proton. So there's a little conversion thing going on there too, since protons and neutrons don't always weigh the same, and when they go into a nucleus, they lose some mass, and we'll talk about that in our nuclear chemistry section. And that's it for this first section. Good luck with your quiz.